All right, good afternoon or good morning or good evening or good midnight, whenever you're listening to this recording. But thank you for joining this air valves class. We're going to be talking about the basic understanding and operation for air valves in water and wastewater systems. And my name is Robert Velasquez, and I work with Simco GC Systems. So today's agenda, what we're going to talk about in this next hour is, first of all, why air valves are needed and used in a water or wastewater system. And then we'll talk about some different types of air valves and the way that they work. We'll talk about air vacuum valves, air release valves, combination valves, and specialty valves. We'll talk a little bit about air valve sizing, and then we'll finish up with some safety accessories. So a little bit about me. I work with Simco GC Systems, and we are a manufacturer's rep, and we work with a couple different lines that you may be familiar with, such as a clay valve and Valvematic and pump tech and safety cover. And then we do some package systems for pressure reducing vaults, and then also we do clay valve maintenance with the service department. So I cover kind of a little bit of Eastern Oregon with Ontario and Baker City, and then Southern Idaho, and some in the Puget Sound in Western Washington. And Steve Cazot, my coworker, covers the rest of Oregon. And so Simco and GC Systems, just give you a little background. So GC Systems is well known for having worked with clay valve for the last 40 years. And Simco is also another waterworks rep that's worked with some companies for the last 40 years in the waterworks industry in the Pacific Northwest. And recently we joined together to create Simco GC Systems. And so we're kind of a new merger company, but we still carry a lot of the same people that came over from GC Systems and Simco, and I come from the Simco side. So why air valves in a water or wastewater system? You might be asking yourself, I work with water, not air. Why do I need an air valve? So, first of all, let's talk about what happens when you don't have an air valve. And I want to play this kind of fun video, and let's make sure that I'm sharing the correct screen. Let's go full screen. So this video right here is of a vacuum test of this cargo container, and they're going to put a vacuum into the steel container and see at what point the vacuum causes some fun things to happen. So here's a little time lapse. They're increasing the vacuum in it, and eventually you get an implosion. The vacuum inside the steel container is pulling in, and when it gets negative below atmospheric pressure begins to push on the outside, which will cause it to eventually implode. It's kind of fun. They show us a bunch of different angles of this, but because of that pressure difference, this container, it can only take about 10 pounds of vacuum. It's made to withstand high pressures from the inside, but not so high pressures on the outside. Let's watch it again. This is nice. It just crinkles up, just sucks in. And then I think they'll give us a good angle on the inside. This is where they're showing at what pressure point it actually, and then you can see the pressure moving all over the place. It's almost like a surge. And we'll talk about that. Here's a good video from the inside of what's going on in this thing, and it just sucks in. All right, let's go back to the presentation. Enough YouTube. The same thing can happen in our water and wastewater systems. The pipes and tanks that we use to store and move water and wastewater, they're made to withstand high pressures on the inside, and they're made to withstand being buried underground. But in vacuum conditions are really tough on those materials. The circle is designed to be strong from the inside, but on the outside, and when it's being pulled in, you get an implosion, and you can get pipe collapse and tank collapse. And this is catastrophic damage where this all needs to be replaced, and you're going to lose service. Another reason for air valves is that when we have a water or wastewater system, and once upon a time, that system didn't have water or wastewater in it. When you get pipe, when you get valves, they don't have water in them. They usually have air in them. And when you put it all together, it's all filled with air. And then you fill it. And when you fill it, most of that air gets pushed out of the end. And that could be through the end of the pipe, or through hydrants or faucets, or when people use water, it gets pushed out. But air is lighter than water. And so air will rise up, and it can get trapped in high spots. And so if air gets trapped in a high point in your line, it's not going to move very easily down and out because it's rising up, and the water is going to push it up and it's going to go underneath it. And even in long runs, the air can get stuck at the top and it won't be able to get out. And when it does that, it can cause restrictions of flow. And so that air pocket will displace the water. So the water has to go around it. And it's as if you have a restriction in the line. And this can cause extra head and extra resistance and friction loss in your water or wastewater system. In addition, those little air pockets, eventually they'll grow so big, they can completely stop and arrest a water or wastewater system, or they can dislodge either part or in whole and move on to the next high point. And when they do that, they can cause sudden changes in velocities and pressures and cause surges in your system. So air is always going to be in our pipeline systems. So we already talked about it, that when we start up our system, there's going to be air in there and you have to get it out. In addition, water contains 2% of air by volume. And that's, how fish breathe. They're breathing with their gills and filtering that air that's in the water. In addition, air can get into your system. It can get sucked into your system if you have vacuum conditions like a surge. If you have a surge and you have a valve, that it can get sucked in, or through maintenance. If you have somebody doing maintenance on your valves, it can get, they put air into the line, they close it all up, and now the air is stuck inside the line. So we're always going to have air, and we need to have a way of dealing with it. Air in a pipeline, in addition, causes some pretty harmful effects. More than, we talked about that, the collapse in the suction, but also corrosion. So corrosion is mainly caused by moisture and air and dissimilar metals. And so you get air pockets inside your pipeline, you got moisture and air, and you can start getting corrosion on that pipeline. Pipeline deficiency, that would mean that you're not getting full flow. It's causing restrictions. So your pipeline systems are designed and sized to get the amount of flow that you need. Now you introduce a whole lot of obstructions with air pockets, and you might not be able to get enough water through your pipes. In addition, that can cause pump inefficiencies because your pumps are designed to push a certain amount of water against a certain amount of resistance. And when you have more resistance, they won't be able to push as much water, and they won't be as efficient in what they're doing. They have to overcome more friction, more push, more pressure against them. Causes surges when they can dislodge and move around, and then also control valve instability. So we work with clay valve control valves, and those are made with the hydraulics of water. And if you get air inside a control valve, it can cause them to be unstable, and it can cause them to not function properly. An additional reason that we put air valves and we use them in water and wastewater systems is because the American Water Works Association recommends it. So they recommend putting an air valve at every point that's a high point, and they determine that by it's a pipe length of change. So if you have one pipe diameter going up and then coming back down, that's a rise. It doesn't have to be super high, but that's where air will collect. In addition, it's recommended that air valves be put on every half mile of straight runs because the friction of air on that pipe will make it so they get stuck and it won't be able to get pushed all the way out. And then in addition, pumps and steep inclines are another point where you want to put valves in to keep from vacuum conditions. Okay, so we need air valves. They provide a pretty critical service of letting air in and out of our pipeline systems, and in order for our systems to work correctly. And so there's different types of air valves. And the different types of air valves do different things. So we have air vacuum valves, and these have large orifices. Air release valves have small orifices. Combination air valves have a combination between a small and a large orifice. And then specialty valves we'll talk about, which is one of those types of valves with additional functionality. So let's talk about air vacuum valves first. So air vacuum valves primarily serve two purposes, and that is that they have a large orifice to let air out of the pipeline system when you start it up, and then they have a large orifice to let air in during a vacuum condition. And the way that they do that is they have a ball on a rod, and that ball works as a float. And it's kind of like your toilet. So you flush the toilet, you open up the bottom, and then you close that bottom. And so the toilet at the upper part has to refill, and you have a ball that's floating on that. And when it pushes it up, it turns off the water supply. This is also really similar to what we have like in a car with your gas tank and your gas meter, or your gas dial. I guess I'm gonna remember what it's called later, but you have a ball basically in your gas tank that's floating up, and you're reading how high that ball is to determine how much gas you have, which is why you always have a little extra gas before your gas meter starts to go down, is because that ball can only go so high, and then the water level or the gas level will go all the way to the top. It takes a little while for that gas level to drop before the ball will start to drop. So anyways, with air vacuum valves, that you've got this ball on a rod so that it's going to be from the forces of gravity down when there's no water in there and there's no pressure. And then when you start up your system, air can escape out of there, and it provides a way for the air to get out. And when water comes up in there, it'll push the ball up, and the ball itself will seat against that large orifice and close it. Now that ball is closed, it's going to remain closed. Even if air collects up inside that air vacuum valve, that air is pressurized at your system pressure. And so it's much stronger than the atmospheric pressure pushing down on the ball and the forces of gravity acting on that ball. If you have 100 pounds of pressure, even air pressure, that's a lot of force. Like think of a 100-mile wind. And so that will keep that ball closed. That ball will only open if the forces of gravity and air pressure pushing down on it are stronger than the pressure in the pipeline system. And that usually means a vacuum. So if you have some type of vacuum condition, then that ball will drop and it'll let air in and keep negative pressures from developing. Let me talk a little bit about surges and filling up your line. So when we start up a water system, you're going to have potential like levels of air inside the system. So we need to exhaust that air. Once we've done that, surges are commonly caused from line breaks and from pump failures. Those are two really common things. So if you have a pump and it's pumping and it's pushing water and it shuts off, it loses power, the PLC fails, the VFD fails or something, and it shuts off, it no longer is pushing water. The water that was pushing will continue to move because it has inertia, but no new water is going to come and take its place. And so because of that, you got force of water pushing away with nothing taking its place, and you can get a separation of water columns, and then you can get negative pressures, because what's going to take the place of that water? And if you don't have anything to take the place of it, you'll get negative pressure, and then that surge oftentimes will reflect back, and it'll come back to fill in that spot, and then you get that swinging water hammer. The goal of an air vacuum valve is that it will allow air out when you start up your system. And then if you have a surge event and that you have a separation of water columns, the air vacuum valve will open up and allow air to take that place, and so that you don't get negative pressure. And then when the surge comes back, it'll push the air out and it'll go through the air vacuum valve. And we have a surge suppression valve I'm going to talk about later that's especially for that. But this is what we're trying to avoid. I was saying earlier, we're trying to avoid that negative pressure from causing the pipeline to collapse. And then now your pipeline is ruined. Another thing that I did mention as well, so pump failure is another common cause of surges. Also line breaks are a common cause of surge. If I've got a reservoir on top of a hill, and then I've got a pipeline that's running steeply down the hill, and at the bottom of that hill, the line breaks or a valve breaks open or something, and water rushes out. I've got gravity pushing that water down, and it's going to push it out, and something needs to take its place. And if the water moves too fast, then you can get negative pressures. And so that's where an air vacuum valve would help put in air, so at least you have something and you don't have negative pressure. So air vac valves, is pretty critical to choose the right size. You need to be able to let air in fast enough to take the place of what the displacement of a surge. And then you also want to look, you want an orifice that's large enough to disperse air when you start up your system, and so that the air doesn't get trapped. And so the orifice on an air vacuum valve is generally the same size as the inlet. So if I have a 2-inch air vacuum valve where it has a 2-inch inlet, it has a 2-inch outlet. Another thing to really touch on with an air vacuum valve is that that float will not open during normal system operation. That float is being pushed closed, and even if the whole thing fills up with entrapped air, that air is pressurized, and so it's going to keep it closed. It'll never open. And so it's not meant to bleed air off of your water system. It's only meant to let air in and out during startup and during vacuum conditions or shutdown. This is an example of a wastewater air vacuum valve. And so it's the same principles where I've got a ball that's floating on the water, but with all of our air air valves for wastewater, we want to keep the wastewater away from our orifices. If that orifice up there gets clogged, then the valve will no longer function. And so we're going to elongate the body, put the float down at the bottom so that it's what's reading your wastewater level. And then we have another ball at the top that is going to seal and seat, and then even a little disc to keep, contaminants, keep anything out of there. And so you're going to see that common theme with wastewater versions of our air and air vacuum valves is they're elongated to keep that wastewater away. Keep it away. That's our main goal. All right, let's talk about air release valves. So air vacuum valves, large orifice, let air in during startup and during shutdown and during surges, but it doesn't bleed air off during operation. Air release valves, on the other hand, they are made to release air continuously under fully pressurized pipeline conditions. And so in order to do that, and in order to accomplish that job, is they have a small orifice. So they have a small hole that's not designed to let air in and out super fast. It's meant and designed to just bleed air off continuously while air collects. And so you get that entrapped air in your water system and it collects into these high spots. It goes up into this valve, and then this valve will just gently bleed it off, and it'll open when it needs to, and then it'll close when it needs to. This is, again, when you have a pump system and you get entrapped air up at the top. Here's a couple examples of different things we're looking at that could be a real problem. So if you have a pump that's pumping water up into a reservoir, and you've sized that pump so that it can push enough water and be strong enough to fill up your reservoir, and then you get an air pocket in some of the high spots in the line, that can cause more resistance, more head loss, more total dynamic head of your system, and cause that pump not to be able to fill up your reservoir. And so it will no longer maybe half full, 3/4 full. You can't fill it up all the way because your pumps aren't strong enough to overcome the added resistance of those air pockets. In addition, with gravity systems, if you have one tank feeding another, you should be able to get a certain amount of fill in the other tank based on gravity. But if you have air pockets that are trapped and suspended air pockets, that will cause more resistance, and you won't be able to fill up the other reservoir as high as you should have been because of those air pockets. So air release valves, they release air slowly and continuously while they're operating. And the way that they do that is that they use a small orifice, and then they use a lever system. And this right here is an example. This picture is of a simple lever air release valve. So you can see there's that little orifice, and then there's that ball, and it's on an arm. And then there's the little rubber, it's kind of that black seat. I think you can see my mouse here. So this little black seat here, that ball is going to float on the water level. And when your water comes up in here, it's going to push that ball up, and it's going to close the orifice. When air collects in here, it'll displace the water, and the water level will drop, so the ball will drop, and it will let air out. And when that lets air out, the water fills back up, and it brings the ball back up, and it closes that. And so we displace that air as the ball drops. And then the way that we can get this to open under a pressurized water system is through a mechanical advantage of our leverage frame. So that's that lever. And the picture here is a simple lever, because you can see it's just connected at one point and it's just one lever. This picture here is an example of a compound lever design where we've got actually two different points of leverage. This would be for higher pressure so that you can create more leverage in order to get this open even under really high pressures. The reason for that mathematically is that the lever is creating more force, and so that we can create more force for this thing to open than what system pressure would be to close it. And so this gets a little heady on the math, but let's walk through this real quick. So if I've got a 1.6 pound float, obviously it takes 1.6 pounds to lift it up. And then it's over a really small orifice. The pressure that's pushing this closed under 150 PSI is the 0.1 for that square inch, because it's really pushing to close it in the square inch. So it's 15 pounds of force. So I could either put a 15-pound float in here, or I can use a lever to make that float heavier than 15 pounds. And so when we put that float on there and we can get a mechanical advantage, we can make a 1.6 pound float actually have 16 pounds of opening force. So that this float here, this thing has more force to open. It's going to drop. And the way that we can get it to close is with water reducing the weight of that float. So with water, we'll float that up, then it has more power to close than it does to open. With an air vacuum valve, we don't have this lever system and we have a big orifice. If we had a 1-inch orifice in here with 150 pounds per square inch of pressure, whew, man, that would be what, 12 inches? So 12 times 150 PSI. So almost, like almost 2,000 pounds of pressure pushing on that ball to close. And so in order to get it to open up during normal operation, you need 2,000 pounds of force pushing it down. And really during normal operations, we don't need to release large amounts of air. You're only going to have small amounts of entrapped air. So you don't need to have this big opening to release air. You need a small opening that can release the air. And so that's how our air release valves are designed. We use fractional, small orifices. And these are sized, I'm going to talk a little bit more about sizing, but these are sized in order to let air out faster than it collects. So we have 3/32, 1/8, 3/16, and that's on the top. A really common misconception with air release valves is that the inlet size is the size of the valve. So I have a 1-inch air release valve and a 2-inch air release valve. The 1-inch is smaller than the 2-inch. That's not necessarily the case. If the 1-inch has a 1/8 orifice and the 2-inch has a 3/32 orifice, the 1-inch actually lets more air out. It really has to do with the plumbing of which one has an inlet size, but the performance is dictated by that orifice size. In addition, there's a plug on top, so you can put a pressure gauge in there and see how much pressure is in your system. And this here is an example of a wastewater air release valve. And again, you can see that we've elongated it out to keep that wastewater away from the orifice. Keep it away, especially with these levers. You don't want anything gumming up those levers, because then you could have an air release valve, excuse me, that gets stuck open. And if it's stuck open, it's going to just bleed, it's just going to be spraying water out. And we don't want that in our wastewater system, especially. So we keep the water away by elongating out the body, dropping that float down farther so that it can sense the water level at the bottom of the valve body. Okay, combination air valves. So combination air valves are exactly what they sound like. They are a combination between air release and air vacuum. So they do both jobs. And these can be installed at high points where you need to have both functions. So you need to be able to let air in and out during startup or during a vacuum condition. And you also need to continuously release air that gets collected up there. So we have different types of combination air valves. And so you can see my mouse here on this left, the far left one, this is a dual body. So it is literally two different valves that are just put together. So I've got an air vacuum valve right here. This is the large orifice with my large float. And then attached to it is a small body air release valve. And this is a compound lever little air release valve with a small orifice. So this here would open and close during startup shutdowns and vacuums. This part here would open to slowly bleed off air while the system is running. This is really common for larger applications. For larger applications is more, we don't have some of these other versions of valves. And so this is also really, this doing dual bodies is very versatile. So I can size the air vac and the air release separately and then connect them together. In the middle, this picture here is a combination combination body. So this float and this stopper here are going to push against this little stem that has a small orifice in it. This little stem is also connected to this piece here, which is essentially a large or a check valve. And so when the system starts up, this check valve will be down and air will go out, and then it'll push it up and it'll close, and that will be held closed. And then this small orifice and this ball and lever will be able to bleed air out of the center of it. This one on the right, this is a combination body. So it is kind of in between the two. So it's one body, but it has two separate mechanisms in it. So this here is the air vacuum, this here is the air release. So our combination air valves, this is what we really would be, this combination body is really, really, really common, especially in 1- and 2-inch sizes. Those smaller applications and distribution systems, you'll see these a lot. And so, as I was saying, this metal stem and check here, this is the air vacuum portion of it. And when you start up the system, air will leave out. And then as water comes up, it'll push this ball up and it'll pressurize and it'll close that. Then when, oh, whoops. Then when air collects in here, this ball will drop, but the check valve part won't. But there's a little tiny orifice through here, and that will bleed the air. Now this is a really, pretty economical because the two are built in together. We don't have these in larger sizes, and they're not as versatile because we don't have as many combinations between the size of the air vacuum and the size of the orifice. You're constrained there a little bit. And that's where we'll see dual bodies used a lot more. This here is the exact same thing, but for wastewater. So again, we've elongated out the body, keeping the wastewater away from the orifice and away from our mechanisms. But the same thing where we've got a check valve here in the top, and then there's going to be a small orifice through it that this ball and float and pad will be opening and closing to continuously release air during system operations. We do also have our air valves, especially for wastewater, with 316 stainless steel and other materials in order to resist corrosion, especially if you have aggressive solvents or chemicals in your system. Here's a kind of interesting little application where we've got two combination air vacuum and air release valves. They're put on a T, and so that they both can work together, and then you can shut one and do maintenance on the other, and so you still have protection from vacuum conditions. All right, let's talk about specialty valves. So as I was saying, specialty valves they're either an air vacuum and air release or a combination, and then they have added functionality. So the first one we're going to talk about is surge suppression. So a surge suppression air valve is a combination air release vacuum valve, but it is meant to suppress surges. So when I was talking earlier, you've got, let's say our pump fails. And so you have the water keeps moving, and then there's nothing to take a spot because the pump it's died. And so you get a separation of water columns, and you need to let air in. That's the vacuum function. So we want to let air in quickly in order to fill that void. When that water column starts to come back, if we just let that air out as fast as possible, there's no resistance against that water column. It's going to come back and slam and water hammer, and then it'll go away. We want to provide some resistance to that. We want to provide some back pressure on that, and we want to control and limit how fast air is released out of the system in surge situations. And so that's what these valves are designed to do. They're meant to suppress air from leaving the pipeline system, and so that we can suppress surges, we can provide back pressure, and we can provide some cushioning. Water doesn't compress. So when you have surge events and water's moving around, it does not compress. It pushes all its force against whatever it hits. Air does compress though. Air works as a cushioning effect. So with these valves here, we can kind of cushion a surge. So this right here would be an example of a dual body combination air vacuum valve with the surge suppression. And that is this feature down here on the bottom. So this feature at the bottom is a check valve that has orifices through it. During normal conditions, startup conditions, air is not moving that fast out of the pipeline system, doesn't push this check valve up, air will go out and it can exit and exit. And when the water level comes up, it'll close, and it'll close your air vacuum, and it'll close your air release, and then it'll close. If we have a surge event and the water leaves and you have negative pressure, this air vac part will open and allow air in quickly. But then when the surge comes back and velocities exceed 8 feet per second, then this check feature here at the bottom will close, and it'll force air to go through the orifices that are inside of it, slowing down how fast the air can exit, providing that suppressing effect, that cushioning effect for the surge. So that is one version. Another version is in this picture here, and that's this red. This red is for wastewater. So we don't want to put a check valve with small orifices at the bottom of a wastewater air combination air valve, right? Because now we're asking for that thing to get clogged up. And if that thing gets clogged up and it doesn't let air out at all, now we've got a lot of problems. So for a wastewater situation, we have what this is called. It's called a red up here. And this at the top, it's what is providing a suppression effect. So it's the same thing on a smaller scale where it has a check valve in there with orifices in it. And so that when air is coming in and coming down, it'll freely flow. But when air is leaving, it'll close the check valve, and the orifices will limit how fast the air can leave this valve, and it can provide that suppression effect on a surge. All right, the next specialty valve we want to talk about is air vacuum valves for vertical pumps. So these are very, very, very similar to the surge suppression valves, but they are just an air vac valve. And these are made for pumps when they start up, especially vertical pumps. There's a lot of air that they're kind of kicking up when they start. And then they're designed to work against pressure. So pumps are designed for, heavy duty pushing something. And when they don't have any back pressure on them, they can cause surges and they can, not function very well. I've got a F-150. I don't have it. I'll be honest here. It's a company F-150. It's really nice. It's got the 3.5 liter turbo boost engine in it. It's got a lot of power. When you're not towing anything, and you're using, rear wheel drive, it has too much power. If you step down on that pedal, you're going to kind of burn out some. So you got to kind of be careful with how fast you push on the pedal. Whereas if I'm towing something, I've got a flatbed trailer out back, then we've got weight on it, and that's how it's meant to be running. Pumps are the same way. They're meant to be pushing against something. And so these valves here are meant to create some resistance. So it's the same principle that we want to regulate how fast air exhausts out of the pipeline. So when we start up our pump, we don't want it to just freely be the air to flow out and for it to just kick the water forward. We want to slow down how fast the air goes out to put some back pressure on that pump. So same thing where we're going to allow air in, but we're going to slow down air going out. So for smaller valves, we use this DPT, which is very similar to the red system, but instead it's using two orifices. So it's got this top here is the vacuum portion where air will flow in through this check valve. But when air is flowing out, that check valve will close. And then we can adjust how closed we want to make this exhaust here. So we can adjust how fast the air exhausts out of the pipeline system. Then on larger sizes, we've got a similar structure to that surge suppression where we've got a check valve at the bottom. Obviously these are for clean water applications, though this DPT could be used in wastewater as well. In addition, neither of these valves has an air release feature. When you're at a pump, there's going to be probably an air release or combination air valve farther down, but this is just an air vacuum. All right, another specialty valve is the vacuum breaker valve. So the vacuum breaker valve is an air vacuum valve that is designed for really aggressive vacuum conditions. This is kind of something that you would put if you're going to have surges. If your system's designed so that when pumps are turning on and such, you're going to have some surge. So you want to put this valve on there because it has a larger body. It allows more flow. And so if you know anything about check valves, we work with check valves as well. You want to get that flow area because you've got this check in there. You need to be able to build around it in order to get full flow. So you can see this body here is expanded out so that when air comes in and this valve drops, it allows a lot of flow. And so this is meant during a vacuum condition to allow a lot of air come in, and it's also more sensitive. Most of our air vacuum valves are meant to open around 5 psi of negative pressure. This one will open with 0.25 psi of vacuum. So it's going to open really quickly, really sensitive, and provide lots of flow in order to break a vacuum condition and keep pressures from going negative. Attached onto this one is a air release valve. So this is, you can put an air release valve on it, but the vacuum breaker is just the air vacuum portion. All right, another specialty valve is the vacuum priming air valve. So this is just a little air valve that's designed to go onto a pump and allow air out of the pump as it's working. So it has a water level control switch and can allow air out of the pumping house and the suction pipe. So this would be like a really common application here. We've got a split case pump here, so we want to allow air out of the casing and we want to let air out of the pipeline. So this little valve here works very well for that application. All right, so we talked about a few different types of air valves. Something to note today, we're talking about AWWA air valves. So don't have any plastic air valves. Those are becoming more popular in the market because they're really light and they're less expensive generally. AWA doesn't approve. They recommend ductile iron body air valves. So that's why we've been talking about these today. Let's talk a little bit about sizing. So sizing of air valves can get pretty technical. There's a lot of math behind it for calculating how fast we need to allow air in and out of pipeline systems. And so sometimes it can get really, if you want to get into the weeds of it on the engineering level, it can get really complicated, but we're not going there today. We're going to just look at some more simplified, and also once you've seen a pipe, you've seen a pipe. So sometimes we can take those, all those formulas, and you just plug in your, simple variables, and then we can get you the right size. So for air release valves, what we're concerned about is sizing the air release valve so that it allows air out as we're operating our system, but it allows air fast enough that it collects. So if you undersize an air release valve, if the orifice is too small, the valve is too small, it's just delaying the inevitable. Because if it can't let air out faster than air is collecting, and it can't catch up with it, then it's just delaying. They'll just keep opening, but the air will collect faster, and then you're going to get in a trapped air pocket, and you're going to get, surges and restriction of flow. So we need to make sure that the orifice is big enough to let air out as it's collecting. Now, on the other hand, we don't want to oversize the air valve. So if we oversize an air valve, like we oversize the weight of the float and the leverage, then it won't be sensitive enough to open. It might be that the closing forces are not strong enough. In addition, another really common thing with oversized air valves is when they burp out water. So they release the air, but they don't react fast enough to the water level. So each time they release air out, they spray water as well. And that's really common. With air release valves, you want to look for the right size orifice. One of the things that we've ran into is when you don't have the right size orifice available, then we'll see a lot of air popping out. And so we work to make sure to get the right size orifice on there. And that's why sometimes the combination air valves work the best, because you can get that air release valve size exactly how you need it, and it's not over or undersized. So when we're sizing an air release valve, some of the important things we want to look at is the flow rate of your mainline size and the pressure of your mainline size. And really the two pieces are affecting two different parts of an air release valve. Flow rate of the main line of your valve, that's affecting how fast air will collect. So you have more flow, there's more water moving past, more entrapped air will collect faster, you need a bigger orifice. Pressure of your main line, that's going to affect the internal mechanisms of your valve. And so if you have really high pressures, you're going to need to be able to open up your air valve. You need, usually a compound lever type of air valve system. Lower pressures, simple lever system will work well. And so that's where we want to make sure that the ball is weighted correctly, and so that our forces work correctly so that it opens and closes based on the water level inside the valve. Here's a little example, kind of using a slide rule. We have these. We also have online calculators. But let's say I'm going to be doing 1,500 gallons per minute, and it's going to be 70 psi. So based on this little slide rule in this chart, for 1,500 gallons per minute, I need a 1/4 inch orifice, because 1,500 gallons a minute is going to cause air to collect up, but a 1/4 inch orifice will allow air to escape faster. Once I know I need a 1/4 inch orifice, now I need to look at an air valve that is that's rated for the PSI range that I'm working at. So I'm looking at 70 PSI. I need one that's rated for more than that, but not too much. So something that's rated for 75 PSI and has a 1/4 inch orifice, you're looking at maybe a 200A. That could be a good selection for an air valve. And so that's kind of what we're looking at as far as sizing our different orifices and sizing our air valve. And that is available in a 1 inch or a 2 inch. And so you want to select the bigger that you can do, but however you want to pipe it. And that's where, the common misconception that, 1 inch is more bigger than a 2 inch and it releases more air. It's not necessarily, it's based on the orifice size. Okay, so air vacuum valve sizing. When we're looking at an air vacuum valve, this is where we're letting air out during pump startup. But the most important thing is we need to allow air in fast enough for a vacuum condition. And so for this application, we're looking at a high point. And so we have a high point of the line, and we're going to put an air vacuum valve on it. We need to be able to allow air in fast enough to account for if there's like a line break at one of the bottoms of these hills. And so we're going to look at what would happen with the separation of these. And so we're going to calculate, well, how much water would move based on the slope and the length of these hills. And if you ever took, like high school physics, then we can break down anything, any movement into horizontal and vertical movement. Any type of angle you're looking at is a triangle. And so we can make two triangles with this. And we say slope A, it is 750 feet and it's a 20-foot drop. And so that would be 0.027. That's our angle on it. Slope B is only a 10-foot drop, but it's also only 250 feet. So it's a 0.04. And then we can, based on a 24-inch pipe, then we can say that, okay, the air that we need to get in there because of these gravitational forces is 18,500 gallons per minute and 22,000 gallons per minute. Interesting enough, slope B, you actually need to let more air in because it's steeper. It may be shorter, but it's steeper. These are all, and this is an example, we have 15,000 gallons per minute pump and the flow rate and it operates at 70 PSI. So that's our two variables there, 15,000 gallons per minute, 70 PSI, we're looking at this hill. Based on that, we know that we need, this is how we're looking at it. These slide rules here are giving us those calculations of 22,000 gallons per minute. And based on that, we're looking at 22,000 gallons per minute, a 6-inch valve. 6-inch air vacuum valve will allow that much flow of air into the pipeline in order to replace the water as it's moving. And then it would move at about a 5 PSI differential. Again, this isn't a vacuum breaker situation. This is a situation of just normal air vacuum valve. Something to note here is that you can use multiple air vacuum valves. So if you calculate all this on a large pipeline system, it may say that you need like a 30-inch air vacuum valve or something. Like that's not going to be economical or realistic. And you don't need one valve. You can do 4 10-inch valves. And this right here, you can see it's on a manifold. And so those all 4 will work together to allow air into your pipeline system. And so that's how, we can get around if the size of your system is pretty large in scale, you can use multiple valves. All right, let's talk a little bit about what type of air valve you need and what type of application. And so, I said earlier that combination air vacuum valves and air release valves, they do the job of both and they're really versatile, and those you'll see most of the time. And a lot of times engineers will spec those in just because it's foolproof. You're not going to put the wrong valve in there. You're going to be able to protect during vacuums and you're going to be able to release air during, normal operation. So it's kind of a win-win. But there are certain instances where you don't need a combination air valve. And so when we're looking at this is kind of a hydraulic line between a pump up to a reservoir. And we need a valve at the pump because that pump's going to be pushing, and when it starts up, it needs to release air. So we're looking at an air vacuum valve on that pump. Don't really need to do air release because it's not a high point. Now, before, you can see here in this line, there's a check valve, and then we're going to go downhill. When we go downhill, we want to have a combination air valve because that's a high point and it's a point where you can get a surge or a vacuum. Then we go down to the bottom, that low point, don't need any air vacuum valve there or any air release valve. And same with 0.4 because it's a low point as well. But once we get up to the top at 0.5, then we need a combination because it's a high point and it's at a slope so you can get a vacuum condition. When we get up to the top, or no, sorry, number 5 is not, it's a air vacuum valve because it's not the high point. 6 is the high point. And so you don't need to collect air right there, but you need to be able to let air in if there's a line break at the bottom or a drain valve opens. Long horizontal run, you're not going to have vacuum conditions that you need to protect against, but you need to release air because it can get trapped along it. So an air release valve could be used there. The next high point before a low downhill, we need a combination air valve to protect against surges or protect against vacuums and provide air release. And it goes on and on. And you can see throughout this whole thing that generally high points, you need an air release or combination air valve. When you have a slope, you need to have an air vacuum valve in order to let air in. And then if you have a long horizontal run, an air release valve is needed to release air out of the system. Okay, let's talk about a couple air valve safety accessories. So we're going to talk about the flood safe, inflow preventer, frost safe, two-way dampener, and the vent safe security cage. First of all, let's just talk about these air valves. So these air valves are put throughout water distribution systems. And when they're put in a pump house, you know, like in this picture that's kind of in the background, you can see that on the right side right here, that is a air vac valve because these are pumps pushing out on these pump control valves. So this air vac valve is letting air out when the pumps start up and letting them in when the pumps turn off or if they were to lose power. Right here in this vault, they're just kind of being piped around and they're just releasing into this pump house because it's just in the house. Now, when we put air vacuum valves in subterranean vaults, we run into some issues. We run into a cross-contamination risk. So if you have an air vacuum valve that's made to let air in and out of a water system and your flood vaults, because how many of you guys have vaults that flood? You know, it's really common. They're underground. They're basically a giant fishbowl. They fill up with water. And so if you were to have your flood vault or your vault flood and you have an air vacuum valve in there and you have a vacuum event, that air vacuum valve is going to open up to let air into the water system. If you've got water in there, it's going to let the water in. And if you've ever been in some of your dirtier vault, you don't want water from there getting into your protected water supply. That is a cross-contamination risk. So you need to make sure that you don't have water coming in during a flood. So one of the common ways to fix this problem that a lot of water districts and engineers did is that you would take the pipe from the top of your air vacuum valve and you just pipe it up out of your air vac, out of your vault, up above ground, and maybe have it like flip around to protect from rainwater getting into it. So that protects now from your vault flooding and getting a cross-contamination risk, right? Yes, but it also prevents a whole nother safety risk. And Homeland Security started looking into this and seeing that you're now providing, when you do that, access to a protected water system to the general public. So you've got this pipe that's up out of the ground and bent around. Somebody were to put water or something containing contaminants or toxins into that pipe and pumped it down into it, the next time that air vacuum valve opens, it would send it right into the water supply. So we don't want to do that either. So another way to do it is that we would pipe a pipe out of our air, out of our vault up to the surface, and then pipe around our air vacuum valve and provide an air break. So you can get air out of there, but air won't come in. And a way to prevent from getting cross-contamination is to then put an inflow preventer. So an inflow preventer is this is a double check assembly that will connect to the exhaust of an air vacuum or combination air valve. And if your vault floods and it fills up with water, it'll raise up the balls on this and that will close off the path. So now you won't get water cross-contaminating into your system. And so these are available to you to be able to protect against cross-contamination, and you can test them as any backflow prevention device. They should be tested annually. So this test box there, you can put a clean water supply in there and raise up the balls and make sure that you don't get water coming out of the nest test cock. Another little safety piece is if you do have a pipe from the surface coming down into your vault, you don't want your air valve to freeze or any of your stuff to freeze down there. So you can put a dampener in that line so that it will dampen the air coming in and out, basically slow down how much air comes in and out and keep you from getting frost and freezing. And then also, if you got a pipe coming up out of the ground, you don't want any critters getting in there or nesting in there. And so you can put it like a little cage. Oh, I guess the title didn't change, but this is our little safety screen cage that can go on there to keep any bugs or animals from getting in there. And this is what an application will look like. So we've got our main line down here at the bottom. We're connecting onto the top of it to pull air out of it. And then we've got a combination air valve here, and it's connected to piping coming out of the top into a flood safe inflow preventer. So this inflow preventer is going to keep, if this vault floods, from water getting into here and causing a cross connection risk. And then we've got a little pipe here and vent in order to let air. And so if you got a pretty big pipeline system, you need your air valve to be able to let a lot of air in. If it's in a vault, that vault also needs to be able to get a lot of air in, or else it could slow it down. You know, if it's got a manhole on there, it's not letting air in very quickly. So we'll have a pipe coming out, put a little vent safe on there, a little frost safe to keep any critters from getting in there and from the stuff freezing down here. So these are just some accessories to help keep your valves safe, your air vacuum combination or air valve safe in your water distribution system. All right, so finally, the benefits of having air valves throughout your water system and installed in the correct spots is that you can increase the efficiency of your pipeline system. By removing those entrapped air pockets and allowing air out of your water system, you can increase the flow capacity of the pipes that you already have. In addition, you have energy savings from increasing your pump's efficiency. So your pumps are designed to push against a certain amount of force. The more force you increase that, the more energy it takes to flow water at the same rate, the more energy you'll use pumping water around. So if we got air valves throughout our water system that are allowing air out and keeping it from getting entrapped and causing restrictions and pressure on the pump, we can be able to move the same amount of water with less energy. Kind of a little interesting concept I remember hearing kind of from an engineer was pumps they're not creating energy, they're converting energy. They're taking the electrical energy and then converting it into hydraulic energy, flow of water. And so if you can be able to get more flow by reducing restrictions, you use less energy. In addition, this can reduce the time that you need to take to fill or drain reservoirs and move water around. If you're trying to turn over your tanks, this can do it more quickly because you can move more water more efficiently. And then also air valves can help reduce water hammer because you're allowing the air out, and when you need to, you're controlling how fast the air goes in and out so that you can reduce water hammer and make your system operate more smoothly. Protects your pipeline from collapse. That's kind of the big one that we started off today looking at, was those catastrophic collapses. And we're going to protect our pipelines with air vacuum and combination air valves in the correct places. And then also if you're doing some type of filter media or you got a plant, if you're doing a water treatment plant, all those things are sized for a certain flow. When you do a backwash, you need to clean out those filters at a certain flow rate. And if you have air pockets that are slowing down the flow rate, you're not going to properly clean them out. So this will help keep everything operating as it was designed to operate. And finally, in conclusion, don't let this happen to your pipeline system. Protect your assets, your underground infrastructure from collapse, from restrictions, from inefficiencies by putting in the correct types of air valves that are sized correctly in your different applications. So thank you guys for attending this class. I might be able to let you out just a couple minutes early. You're welcome. But here's my contact information if you ever want to give me a call. And Steve, so I should put his contact information. He'll be, him and I are teaching a control valve class. So if you want to get us information from that class as well. And feel free to give us a call. If you have an application with an air valve or a combination or air vac and you're looking for recommendations or sizing help or just double checking, let us know. We can take a look at it and make sure that you're protecting your pipeline system and you're getting the most out of your water infrastructure system. So thank you guys so much and have a great day.